Hi everybody, and this is Rings and Isomers. So we'll start with rings. Rings are interesting, and carbon is very adaptable. So as we can see, it can make single bonds, double bonds, triple bonds. It also can wrap around on itself to make what we call a ring. A ring we don't usually show as being circular. We show it as polygons with hard edges, and they can range from 3 to 30 carbons big. But the most common ones we'll see are 4 to 6, although we might see a 3 or a 7 occasionally, but mostly 4 to 6 are the ones that are most common. So all the corners in a ring are representing carbons, and the H's are implied in the ring. So we don't actually have to show the H's when we do the ring. If we have substituents, we'll show H's on them, but in the ring itself, we'll just show the C's as the corners, and you'll see what I mean in a moment. So at the top, the pictures here show us sort of the more complete form. So if I had a 3-carbon ring, the carbons would form a triangle. Each carbon needs 4 bonds, so they would each have 2 H's each, and that's sort of more or less what it looks like. Coming over to the second structure, we've got 4 carbons all arranged to meet each other so they make a square. And again, that's sort of more or less what it looks like. But instead of drawing them like this where it's quite complicated, if I were drawing a 3-carbon ring, I would instead simply draw a triangle. And this will represent a 3-carbon ring. Same thing here. If I had a 4-carbon ring, I would simply draw a square. And that's, again, what I would do. And then I could put substituents on, I can put multiple bonds on, etc. So here, the pictures show you from 3 up to 7 carbons in a ring formation. We're going to draw them as these shapes, and then we'll put on additional information as we need it. When we're drawing substituents, there's no beginning or end in a ring. So you can decide who your number 1 carbon is going to be. I usually make the top one my number 1, and then I typically will go clockwise, although you can go clockwise or counterclockwise. When it comes to naming, you saw a little preview in the previous couple of slides. The word cyclo goes in front of the parent chain, and that tells us that we have made a ring. So if I have a pentane, that's 5 carbons in a row. If I have a cyclopentane, that's 5 carbons attached to themselves. When we're numbering the ring, we can go clockwise or counterclockwise, but our goal here is lowest overall numbers for substituents, just like it is when we do a straight chain. Because there's no number 1 location, we're going to put our number 1 where there's a substituent. And typically, we're going to try to give larger substituents a lower number if possible. We can do this more often with rings than with straight lines, although that rule does apply to a straight line as well, but we're going to more see this with rings. The other thing is, if I have a multiple bond, it's the boss, just like it is with a straight chain. So if I did get a multiple bond, I would give it the lowest number. And I have to make sure I'm really cognizant of going between the 2 lowest numbers for a double bond. I'll give you an example here. Let's say that I had a 4-carbon ring, and I have a double bond here. Notice we just put a line there. That's all we do. If I were numbering, I could do 1, 2, or I could do 1, 2. What I can't do is say 1, 2. I have to have the double bond between the 2 lowest numbers. And if I start something like this, you'll notice when I come around between the double bond, it's now 1, 4. So that's something I can't do. It has to be between the 2 lowest numbers. So I can arrange them going from the top to the bottom or the bottom to the top, depending on whether my goal is to get to a substituent, etc. You'll see me do that as we go. So let's do some examples. So our first example, you're going to draw a methyl cyclopentane. So again, we're going to start with the parent, and it's a cyclopentane. So I'm going to do a 5-carbon structure. It's not beautiful, but it'll work. And they are wrapped in a ring. So again, cyclo means ring, pent means 5 carbons, and pentane means they're all singly bonded to each other. Now I'm going to put a methyl in. There's no number here, which means it's the number 1 location. And my ring, any one of these could be number 1. There is no left and right. There's no beginning and end in a ring. So typically I put my number 1 at the top, but it doesn't make any difference. You can put it on any of the corners, and that by default will then be your number 1 corner. Let's try this one next. So the parent is going to be a cyclohexane this time. The tricky bit about this one is going to be numbering. Remember that I want overall lowest number for my substituents, and if I can give a big substituent the lowest number, I will. Here though, because there's a grouping of substituents at the top, it's better to go with overall lowest. There's a couple of options here. I can go 1, 2, 3, 4, 5, 6. That would be one option. I'm just going to switch colors here. Let's go orange. Or I could do sort of 1, 2, 3, 4, 5, 6. Oh, shoot, that was the same thing. Do over. I could do something like this. 1, 2, 3, 4, 5, 6. The inside numbers, I would end up getting the combination of 1, 2, and 4 for my substituents. And if I use the outside numbers, I'm going to get 1, 3, and 4. So if I actually add them up, I can see which one's better. So 1 plus 3 plus 4 makes 8 here. And then down at the bottom, 1 plus 2 plus 4 makes 7 here. So the inside numbering is better. It's overall lowest. And you probably could figure that out without this conversation, but sometimes you can't, so I wanted to show it to you. So let's put it all together. So we are going to have a 1, 2 dimethyl. Oh, I totally screwed this up. Back it up. All right, who can tell me what I just did wrong? Alpha order, folks. Alpha order by substituent name. So, not numerical order. 4-ethyl, just keeping it real over here. 4-ethyl, 1, 2 dimethyl. And again, some of you might have thought, oh, that's right, because di starts with a D. But when I'm doing alphabetical order, it's by substituent name. Eth becomes before meth. And then cyclohexane. I probably do these mistakes on purpose just so you can learn from them. All right, let's try another one. So I've added in a double bond this time, and again, the trick with this one is going to be working out numbering. So the parent is going to be a cyclopentene, cyclo meaning ring, pent meaning 5 in the ring, and ene meaning double bond somewhere. And again, my double bond has to take priority. So I really only have two choices with numbering. I can do this number, 3, 4, 5, or I can go around this way, 1, 2, 3, 4, 5. Again, the double bond has to be between the 1 and the 2. So the red numbers on the outside are actually the better option because that gets me to my substituent as quickly as possible, and that's always going to be my priority there. So we'll use the outside numbering here, and let's put it all together. So I'm going to have a 3-methyl, and then I have a 1-cyclopentene. I don't have to include the 1 because it's a 1. So I could just say cyclopentene here. But I could also put a 3-methyl 1-cyclopentene here too. So you have your choice whether you want to keep that 1 or not. I'll leave that up to you. Let's finish up with a challenging one here, and then we'll do our second topic, which is isomers. So again, I have a ring structure. It's 6 corners, so a 6-carbon ring. So I have a cyclohexene, but I have 2 double bonds. So I actually have to say that I've got 2 double bonds. And if we look at the part of the name that means double bond, it's this part right here. So what I'm going to do is I'm going to put the di before the ene. If I put the di in front of hex, that means 2 times 6 carbon rings. Or in front of the cyclo, same thing. I'd have 2 times 6 carbon rings. It's only the ene, the double bond, that's actually duplicated. So that's where I'm going to put the di. The other thing I wanted to show you with this example is how 2 substituents can share the same corner. You can put 1 substituent inside the ring if you wish, but it gets a little crowded. So typically if 2 substituents are sharing a corner, we just sort of separate them out to the sides like this. So let's decide how our numbering is going to work. Again, we want to make sure both double bonds get the lowest possible numbers, and we also want to get to the substituents as quickly as possible. So lots of choices here, but I think this choice will probably be the best because it gives us a 1,3 location for substituents. And then it gets to our substituents, or 1,3, sorry, location for our double bonds, and gets to our substituents as fast as possible. You can play around with the numbering, but I think this will work out the best. Let's put it all together. So we've got 5, 5 dimethyls. We are going to use numbers here this time because we have multiple numbers. So we're going to call it 1, 3, always the lowest of the numbers between the two chains, or the double bond rather. So 1, 3, cyclo, hex, and sometimes we put an A in here just for flow, so hexadiene. And if you didn't include that A, I wouldn't be offended, but we usually put an A in there just so it flows a bit better. Otherwise it's hexadiene, it's a bit choppy. All right, moving on to topic number 2 today, and that is isomers. So we have 2 different types of isomers, and the first one's called a structural isomer. And you can draw this for anything, a double bond, a triple bond, substituents, no substituents, like all kinds of stuff. Anything can have a structural isomer. Basically what happens with a structural isomer is it has to have the same formula as its as any drawing. So any isomers have the same formula as each other, but they're put together differently. So we're going to try this first example. I should have given myself a little more space for this, but we're going to try the first example, C6H14. And I'm just going to check to see what kind of thing it is. So it is going to be a CnH2n plus 2, which means it's an alkane. So I'm going to do 3 isomers, and the only rule is that they have to have 6 carbons and 14 H's, and they have to be alkanes, because I just worked out that that's what the formula tells me. And so I can keep it as simple as I like. So the first one, I'm just going to do the carbon bit of it. I'm going to do 6 carbons in a row. That's the easiest alkane, or isomer. 1, 2, 3, 4, 5, 6. So that would just be a hexane. If I want to do an isomer of this, I still have to maintain 6 carbons and 14 H's. I'm not going to bother with the H's right now because I don't have a lot of space, but if you make sure it's an alkane, they'll work out. So I can't really do anything else with 6 in a row, but what if we did 5 in a row? 1, 2, 3, 4, 5, and we picked up the 6th one and made it a substituent. Now I've got something new. Because these two have different names and they're different structures, they are different from each other, but they are also isomers of each other because they have the same formula. So that's what makes them isomers. Let's try to make one more isomer. Let's pick up 1, 2, 3, 4, 5. Let's pick up that substituent and put it on the number 3 carbon now. They are all 3 things different from one another, but they all have the same formula, so they're all isomers of one another. If we were to move the carbon over one more location, would that be something new? The answer is no. If I were to put the carbon in this location and draw a 4th isomer, that would be identical to our second isomer, because if I put the carbon to the right, I would end up numbering from the right-hand side instead of the left, but they would have the exact same isomer. So I've kind of run out of isomers with a 5 carbon chain, and I'm only asked to make 3 anyways, but just to show you, I could make another one. I could go down to 4 carbons, for instance, and now I have 2 extras, and I could put them like this. Or I could go down to 4, and I could put 1 up, 1 down. I think that's all the isomers I can make. The more carbons we have to play with, the more options that I have here. Let's try another example. This one is very similar, but it's not giving us a general formula, it's giving us an actual molecule. So it says draw 3 isomers of 2,3-dimethylhexene. Our first job then is going to be to see what the heck does 2,3-dimethylhexene look like. So let's draw this out. So starting with my parent chain, I've got 6 in a row. 1, 2, 3, 4, 5, 6. And it's got an ene. There is no number in front of here, so that means the double bond is in the front. Now I've got a 2,3-dimethyl, so 2,3-dimethyl. There's my carbons. So if I count all the carbons then, I've got C8. Because there's a double bond, I know my general formula is H16, so CnH2n. So that's my general formula, and that's what I've got to stick to when I make my 3 isomers. So isomer number 1, basically the rules are this. I have to have 8 carbons, I have to have 1 double bond. So let's keep it simple. 1, 2, 3, 4, 5, 6, 7, 8. And let's put the double bond in the first location. The more complicated the original structure is, the easier it is to make isomers. Because I can now make a second isomer, 1, 2, 3, 4, 5, 6, 7, 8, and by moving the double bond over one more, I've now got another isomer. So I can keep doing that. I can just keep moving the double bond over and make a bunch of isomers. I can also shorten the parent chain, pick up the extra carbons, and make substituents. So I can make things really complicated too. So for instance, 1, 2, 3, 4, 5, 6. Let's put the double bond in the number 3 location just for fun. I've got 2 more carbons. Let's put 1 here and 1 here. There's 3 isomers. I can make tons of different isomers here because not only can I move my double bond around, but I can shorten the chain and put my substituents around. One thing you want to be mindful of is don't put a substituent on a number 1 carbon because that's just an extension of the parent chain. Let me show you in green. So let's say I had 1, 2, 3, 4, 5, 6. I'm going to do similar to what I just did. Let's say I put the carbon here and here. You've actually just got a big old bent big parent chain. Now that's okay. It could be something new that you've drawn because you actually haven't drawn anything like that so far in red, but you might end up disguising an isomer on yourself. I left this extra one. I should have left this one more at the beginning, but we're just going to skip by this guy. All right, let's look at type 2. Type 2 are geometric isomers. So geometric isomers are very particular. In order to have a geometric isomer, you have to have a double bond, and you have to have only 1 hydrogen for each of the carbons on that double bond. If you do not have this criteria, you cannot have geometric isomers. The reason why you have a geometric isomer here is because there's no rotation through a double bond, which means up and down makes a difference. So for instance, if you had a double bonded, let's say we had an H here and an H here, up and down makes a difference. So you can't actually rotate this double bond like a single bond. Single bonds can rotate freely. If you put your thumbs together and then put your pointer fingers together and then you try to put one of your hands upside down without breaking this double bond that you've created between your thumbs and your fingers, you can't do it. That's what's happening here. So this is one option, but the second option would be to have this. This is the same as both down because I can just flip it upside down. But to get them to actually be on up, one down, that means I actually have to break the bond and reorganize it. So again, these are what geometric isomers are all about. When both the H's are on the same side, so they're both up or both down, we call that the cis isomer. And when the H's are on opposite sides, one's up and one's down, we call that the trans isomer. So let's do an example. So the first one says to draw the cis and trans isomers of 2-pentene. I'm going to just draw 2-pentene to start. 1, 2, 3, 4, 5. Number 2 has the double bond. I'm going to just show the H's like this for us. You can tuck them in as well, that's fine. So the way the H's work here is I'm going to show them like this. Now normally I tuck my H's in, so let's do the 2 examples down below. So for the first one, let's do a cis 2-pentene. That's similar to what I've just drawn. CH3, C double bond C. I'm going to pull the H's out to show them on the same side, either both up or both down. The other ones, oops, I forgot an H over here. The other ones, I'm just going to tuck them in. The other version is, let's do it in green, trans 2-pentene. And again, CH3, C double bond C, CH2, CH2, CH3. I'm running out of space. But trans tells me pull the H's out and put them one up, one down. The next example is name the following. So this one's kind of funny because it's actually using Vesper shapes. We know all the different shapes because of our unit in structure, but we don't show them in organic. Organic, the focal point is in terms of the bonding. So here, my longest carbon chain is through here. So this is actually a butene. And the double bond, if we number from left or right, it doesn't make a difference. It's symmetrical, so it's a 2-butene. And because both the H's are on the same side, this is going to be a cis. So let's put it all together. So I've got a cis 2-butene. And again, in terms of numbering, there's my number 1, 2, 3, 4, or I could number it exactly the same way from the left and it would still be the same thing.